All right, so we've been talking about functions, and so today we're going to look at some more specific things about functions and their graphs. And we're also going to learn how to graph piecewise functions, in other words, functions that are in pieces. All right, so the first category that we have is we can tell some things about the symmetry of a graph. So there are three main types of symmetry that we're going to discuss. They are not the only three types of symmetry out there, but they are the three main ones. All right, so the first type of symmetry is x-axis symmetry. Then we have y-axis symmetry. Space these out because we're going to draw some graphs under them. And then the most difficult to kind of eyeball and tell is origin symmetry. All right, so x-axis symmetry looks like this. Okay, you have an axis, and then your graph is cut in half by the x-axis. Okay, so that is what an x-axis symmetry graph looks like. But here's how you're going to be able to determine if something will have x-axis symmetry before you graph it. You're going to replace y with negative y, and you're going to simplify. And if the new equation equals the old equation, then it means that you have x-axis symmetry. So I'm going to abbreviate symmetry here. Okay, so we're going to look at an example, but this is what it will look like if it has x-axis symmetry, okay, or something like it. This is how you're going to show if it's supposed to have that type of symmetry or not, like if maybe you're not looking at a graph ahead of time. So y-axis symmetry, not surprisingly, the y-axis cuts it in half. Remember, this is one of our common functions that I handed out in a handout, right? It's the absolute value graph. But here's how you're going to know that a graph would have this type of symmetry. You're going to replace x with negative x. And again, you're going to simplify. Okay, by the way, I'm going to underline this term simplify. It's actually one of the most important pieces of the puzzle here. Okay, you have to simplify it in order to compare. And then if the new equation equals the old equation, then you have y-axis symmetry. And then lastly, we have origin symmetry. This is the most difficult to pick out. But origin symmetry looks like this, like half of the piece looks like the other half that has been, you can describe it one of two ways. You can either talk about maybe this half rotating 180 degrees around to this half, or you can talk about folding this half over the y-axis and then over the x-axis, or the other way, folding it over the x-axis and then folding it over the y-axis. Okay. Either way, it looks like this. It looks like half of the figure kind of got spun around and turned the other direction. And how we're going to show this algebraically is you're going to replace both x and y with negative x and negative y. And again, you're going to simplify. That's always an important step. And then again, if the new equation equals the old equation, then it has origin symmetry. Okay, so let's talk about what kind of questions you can expect on the first exam, what kind of questions you can expect on Connect. So you might have a question that says, tell me what kind of symmetry, if any, the following function has. Now, FYI, you can have all three of these types of symmetry. You can have one or two of them. You can have none of them. So just because you've shown one of them doesn't mean you stop. Okay, you actually need to test for all of them. So we're going to ask ourselves, does it have x-axis symmetry? Does it have y-axis symmetry? Does it have origin symmetry? And then we're going to show the work for that. Okay, so remember, for x and y-axis symmetry, you just take the other variable and you replace it with the negative version. So because we want x-axis symmetry, we're going to replace y with negative y, but we're going to leave x alone. Okay, but now we want to simplify. In other words, we want to talk about how we can easier write this term right here. Okay, notice if you have a negative something times itself 4 times, a negative times a negative times a negative times a negative would be a positive. So this is y to the 4th equals 2 plus x squared. Okay, and then what you do with this is you compare to the original. And hopefully you see that the original, it's exactly the same, right? So because it's the same, then that means, yes, it has x-axis symmetry. Here, right there. Okay, so that means if we drew a graph of this, which we probably wouldn't because of how it looks, but if we did, it would have x-axis symmetry. Okay, so now let's move on to y-axis symmetry. So for that, we leave y the same, but we replace x with the negative version of itself. And then again, we want to simplify the part where we made a change. Okay, and notice same logic as the first one. If you multiply a negative times itself 2 times, you're going to get a positive. So we've got y to the 4th equals 2 plus x squared again. Okay, notice we're also going to compare this to the original. And what I think we can notice is, again, it's the same. So remember how I said it could have more than one type of symmetry? So in this case, yes, it has y-axis symmetry. Okay. If you don't get the exact same equation again, like a sign is off or something like that, then you're going to say no, it doesn't have that type of symmetry. And then for the last origin type of symmetry, remember for x and y, we set the other variable equal to the negative version of itself. For origin symmetry, we do both. Okay, we replace both y with negative y, but also x with negative x. Okay, and then again we simplify, but notice we have 2 things to simplify this time. So same logic as before, these are going to turn into the positive versions of themselves. Notice if we had odd powers, that wouldn't be happening, because if you multiply a negative times itself an odd number of times, it stays negative. Okay, but then we're going to compare to the original. And notice, just kind of a fluke thing, this doesn't happen always, but it actually has all 3 types of symmetry. So don't expect that the ones on Connect will be necessarily this result every time. Okay, so it can have a combination of the 3 types. It can have a couple of them. It can have none of them. Okay, just make sure you are showing your work in the following way that I showed you right here. Okay, or in the previous way. In other words, on Connect, it's probably just going to ask you whether it has x-axis symmetry, yes or no. Y-axis symmetry, yes or no. Origin symmetry, yes or no. So if you want to cheat the system, you technically could just guess your answer, but that's not going to prepare you for a test. Okay, and remember, the main determinant of your grade in this class is not the homework, it's the tests. Okay, so you want to practice your homework like you'll be expected to show it on tests. Okay, so another detail about functions that we're going to break into today is that functions can be either even, odd, or if they are neither one of those things, they're considered neither. So let's define what even functions are. So here's your math book's definition, okay, your ebook on Connect. If f of x equals f of negative x, then f of x is considered to be even. Okay, so that's a really short way of describing it, but the everyday language to describe what you'll do is basically you're going to replace x with negative x, And you're going to simplify much like we did for symmetry above. And if the new equation, I'm going to abbreviate equation like that because I'm tired of writing out the term equation. If the new equation equals the old equation, then the function is even. So you're going to find the negative version of the original, and if it ends up being the same as what the original was, then the function's even. So what about odd? So the book's definition for odd is that if you have f of negative x and it's equal to negative f of x, then the function was odd. So the everyday explanation of this is that you're going to replace x with negative x again. Notice what we do is the same for both of them and simplify. The only thing that's different is kind of the result you get. And so if it's going to be odd, then the new equation is going to be the negative version of the old equation. And then we know the function is odd. So rather than it being exactly the same as what we started with, we will have the negative version. All right, so again, kind of like I said on the last set of problems, Connect is probably just going to ask you even, odd, or neither. So if you make a random guess, you have a 1 in 3 shot of getting it right, but that is not going to be sufficient on an exam or a quiz. So just make sure that you practice it algebraically like we're doing here. All right, so we didn't really talk about neither, but it kind of stands to reason, right? If it's neither even nor odd, then we're going to say it's neither. Okay, so like if it's not the same when you're done, if the new equation is not equal to the old equation, or if the new equation isn't equal to the negative version of the original, then it's not either one, and we would say neither. All right, so let's do a function that on first glance might look a little complicated. So let's look at negative x to the 8th plus the absolute value of 3x. Okay, so is this even, odd, or neither? That's the question. So to show this, you have to find g of negative x. Okay, in other words, replace every x with a negative version of itself. Okay, and then we want to simplify. Okay, so I'm going to go kind of slow here, but be really careful right here where I'm pointing. You would not say, oh, a negative times a negative is a positive, because actually you're not allowed to do that until you've determined what the exponent is first. In other words, we don't pay attention to that sign right there. We determine what the exponent is, so let's think about that. Negative x times itself an 8 number of times any even number of times would be positive, right? So that's going to be positive x to the 8th, and then you're going to apply the negative. So you have to do order of operations, and order of operations says to do the exponent first and then worry about that negative sign on the outside, okay? And then what about absolute value? Absolute value means always that we're finding the positive value, okay? So the absolute value of this is just the same as the positive version, okay? And then what you're supposed to do with this is you compare it back to here. Okay, and when you compare it, notice that it is the same. So that means f of x is even, or sorry, g of x in this case. Okay, so notice for showing even, it's kind of similar to the symmetry thing. We'll talk about that in a minute. Odd is just a little bit different, so let's look at another one. So again, even, odd, or neither. So let's say this is the function I want you to look at. So notice we don't really know whether it's even, odd, or neither, and we don't need to. We've used the same method to show any of these. So you always find f or k in this case of the negative version of x. So everywhere there's an x, let's replace it with a negative x, and then we're going to simplify it. Okay, just make sure you really think about the simplification, right? I should be doing exponents first, so negative x times itself 3 times, notice that's an odd number of times, would stay negative, okay? So this would actually be negative 13x cubed, because the power doesn't change, and then a positive times a negative here is also a negative. Okay, so the point is not so much what you get, it's what do you get compared to what you started with. Okay, so notice they are not the same. Okay, they are not the same, so they are not even. Okay, so the next thing is this function the negative of the original? Okay, and notice that all signs change. Okay, which means it is the negative of the original. Okay, so that means that it is odd. Okay, so you just have to be able to show that it is the exact negative version of the original. Now, for a problem like this, if you would have had some of the signs change and some of them not change, then you would have to say neither, okay? Because the negative version needs to truly be the negative version everywhere, not just in some places. All right, so one more of these, and then we're going to talk about what even, odd, or neither tells us about the graph of our functions. All right, so let's look at this ugly guy. Square root of 81 minus parentheses x plus 2 squared. So I know this one looks ugly, but we don't start it off any different. Okay, we need to find r of negative x. So we need to do 81 minus parentheses negative x plus 2 squared. For the same reason that we mentioned before, you would not simplify this minus sign here. Okay, you're not allowed to do that because of the squared. You actually would need to mess with the squared first. You would need to FOIL. Okay, so what I want you to notice is if you compare this to the original, by the way, there's no simplification you can really do here without making it more difficult, which is kind of the opposite of simplifying. Okay, so you're going to compare to the original, right? And what I hope you notice is that it is not the same. Okay, and it is also not the negative version of the original. Okay, so the fact that it's not the same means it's not even. The fact that it's not the negative version of the original, by the way, what that should have looked like is just a negative sign out to the front, okay? Because this term is kind of all grouped inside this square root. So since neither one of those things happened, we'll say it's neither. Okay, so if what you get is exactly the same as the original, it's even. If what you get is the negative version of the original, it's odd. And if neither one of those things happen, then it's neither. Okay, so that's how we algebraically show that functions are even, odd, or neither. If we have a graph, we can also graphically show. So it turns out that even functions have y-axis symmetry. I meant to say y-axis symmetry there. Okay, and we kind of touched on that when we looked at symmetry, right? If you look back at y-axis symmetry, how you show that is you replace x with negative x, which is exactly what we've been doing for even, odd, or neither. So, for instance, if you were to see a graph that looks like this, then you would know that this is even because it has y-axis symmetry. Okay. Odd functions, on the other hand, have origin symmetry. So let's look at probably one of the more popular odd functions. So one of the graphs on your common sheet that we handed out was the x cubed graph. Okay, and it's odd because notice just what we said, that this piece is a rotated version of this piece. Okay, so this would be odd. Okay, so I want you to be able to One, tell if something's even, odd, or neither based on the equation itself. That's the algebraic version. And then also, if you are given a graph, you should be able to tell whether it is even or odd based on what the graph looks like. Okay. And by the way, neither functions, I won't say they're not symmetrical because that's not true. Okay. But neither functions have neither of these types of symmetry. So you can still have a graph that has some symmetry. It just won't have y-axis or origin symmetry. So another way to say that is if you shifted this parabola to the left, it would no longer be even because it would not have y-axis symmetry anymore. Okay? So unless it's centered perfectly at 0, 0, it's not going to be even. Okay? So you can have a parabola that would not be considered even because it was shifted over either left or right. And so in that case, a parabola shifted left or right that didn't have y-axis symmetry would be neither. Okay, so as a general rule, you can't just look at what the powers are. That's not enough to tell whether it's even, odd, or neither. Okay, so next let's look at a special group of functions called a piecewise function. Okay, piecewise functions are just like they sound. They are functions that are pieced together. But piecewise functions naturally occur in everyday numbers all the time. Okay, all they do is represent a change in pattern. Okay, actually let's look at what the equation looks like first and then we'll graph it. So here is how piecewise functions look. Rather than just being f of x equals 1 equation, typically you have more than one. So usually you have a curly brace, just an open curly brace. So maybe the function is 1 when x is less than -1, but maybe the pattern switches to x when x is greater than or equal to -1. Okay. So notice this just represents two functions or two patterns. We use the first function when x is less than -1, and we switch to the second function when x is greater than or equal to -1. Okay, so this is what equation form looks like for piecewise functions. Okay, and it can have more than two, okay, but most of the ones we'll do will only have two, especially the ones where we're going to graph it. So here's what the graph would be, and let's see if we can kind of piece this piecewise graph together. So let's go out 4 in every direction. So notice it tells you that y stays steady at 1 until you hit -1, x equals -1. So in other words, we're going to stay steady at -1, but right at x equals -1, we're going to have an open circle, and then this way we're going to stay steady at -1. Okay. So notice we're 1, 1, 1, 1 all the way up until we hit x equals -1, and then we stop. Okay. Notice I used an open circle because it was just plain old less than -1. If it were less than or equal to -1, I would use a solid circle. Okay. So we start off as a constant pattern, but then we switch to a linear pattern. Okay. So at -1, we start switching to a line with a slope of 1, essentially. Okay, so notice this represents the two pieces, right? This is piece 1, and this is piece 2. Now in a minute we're going to practice graphing these on your own, so if you don't know how I came up with that, I'm going to show you how you can come up with that on your own. So this is the graph form of a piecewise function. Okay, so sometimes piecewise functions look like separate pieces, and sometimes they're actually going to be pieces that are joined together, and we'll look at both of those when we get to graphing. So let's look at one more, though, with just an equation form. So this time we're going to stack 3 equations in f of x. So here are the 3 patterns / equations: -3x plus 7, x squared plus 3, and 5. And that curly brace just means, hey, include all 3 of these equations together. All right, so this one's going to be for x is less than -1. This is going to be for -1 is less than or equal to x, and that's less than 4. And then finally, this one's going to be for greater than or equal to 4. Remember, you can pause the video anytime you need to catch up on the writing, right? That's the beauty of watching a lecture video instead of watching it live, right? You can pause it whenever you need to. So let's read through these. This first one says x is less than -1. So anytime x is less than -1, we need to use the first pattern. Okay. Don't overcomplicate this. It literally looks just like you would kind of read it from left to right. In other words, it looks like x is sandwiched between -1 and 4, and that's exactly what it means. It means anything between -1 and 4. Okay. But notice we're including -1 because of that or equal to symbol, but we're not including 4. Okay. And then here, of course, we'd read that one as x is greater than 4. So let's say I gave you 3 function values I wanted you to find. So f of 3, f of 4, and f of -2. Okay. Notice before when we did these last week, f of something just means go plug that in, right? But the question becomes, well, which one, right? Like which equation should I be using to plug it in? And it all has to do with whatever your x value is at that spot. So notice here my x is 3. So you just kind of run through the list. Is the x I'm using in part A less than -1, right? So is 3 less than -1? Definitely not, right? So I don't use that equation. Move on to option number 2. Is 3 in between -1 and 4? Okay, the answer to that is yes, right? So I will use equation 2. Since 3 is between -1 and 4. Okay, so once I've decided which equation to use, it's just like the plug-in question. So I'm going to do 3 squared plus 3. Make sure you square before you add, right? So I'd have 9 plus 3, which is 12. Okay. By the way, this is still the y value when x is 3. Okay, so that hasn't changed. Okay. All right, so let's move on to the second one. Okay, this time x is 4. So again, we're going to run through our list. Is our x value less than -1? The answer is no, right? Is it between -1 and 4? That's a little iffy, right? But notice this does not actually include 4 itself. So that's a no for this one. Notice this is greater than or equal to 4, right? So we would use equation 3. And that's because 4 is greater than or equal to 4. Okay. Notice this is not an interesting function, right? There's nothing really to plug in here. It's just that the answer is 5. Anytime you're using equation 3, the answer for y is just 5. And then last but not least, let's try -2. Okay, so again, we evaluate what our x is, right? So we go down the list. Is -2 less than -1? Okay, and notice it is, right? So we would use equation 1. And that is since -2 is less than -1. So we would plug in -2, so we get -3 times -2 plus 7. So 6 plus 7 is 13. Okay. So notice these are all still y values. F of something just means the y value. Okay. So notice what we didn't do, which I see students do a lot. Okay. We did not plug it into all 3 and then try to figure out which one we were going to keep as our answer. In fact, with a function, you're not allowed to do that because that means you're repeating your x value. Okay. So what you do is make a decision on which equation it's appropriate to use first, and then it's just a plug-in problem. Okay. So once you've made that decision, it's actually pretty easy peasy. Okay, so let's practice graphing a couple of these. So you know it's piecewise when you see a curly brace and more than one equation written out. Okay, so we're going to have clearly two pieces to our graph, right? It is definitely easier if you go through and try to figure out what types of pieces you can expect. In other words, x to the first power graphs, remember we talked about when we talked about the graphs of common functions, x to the first power graphs are always going to be lines. And then what about x squared? Those are always going to be parabolas. So this is going to be two pieces of a graph, one that's a line and one that's a parabola. Okay. So early in their semester, when we didn't know how to graph something, you can always do what I call an XY table. Okay. But for this, I'm actually going to do two of them because I have two pieces. I want to graph the line separately from the parabola, and so I'm going to do it this way. So for this chart, I'm going to stick with things that are less than or equal to 0. And for this chart, I'm going to stick with things that are greater than 0. Okay? And by the way, this is the graph that's going to show me the line, and this is the graph that's going to show me the parabola. Okay? So notice I can't just pick any x's I want. I need to stick with x's that are less than or equal to 0. Okay? So some things that are less than or equal to 0 might be like -2, -1. Always go right up to the edge, so you want to pick 0 in this case. In other words, pick the actual ending point there. Okay, so let's plug those in and plug them into the line equation, right? So -2 plus 2 is 0, -1 plus 2 is 1, 0 plus 2 is 2. So I'm going to kind of graph this as I go. So let's go out, I think maybe going out 3 will be enough. We'll always extend it if we need to. So I've got the point -2, 0, -1, 1, and 0, 2. Notice 0, 2 is where I stop, right? And so notice I have my line. Okay, so that is a piece to my piecewise function. Okay, but I stopped at 0 because I'm not supposed to be going over 0, right? When I go over 0, I'm supposed to switch to this graph. Okay, so now let's pick some points for the parabola. It might surprise you maybe a little bit, but I want to pick things that are bigger than 0, but I'm also going to pick 0 itself. Even though 0 is not technically included here, I need to get right up to 0, and I need to make sure I give myself a note that although this is going to be an open circle, it's not actually going to be part of the graph. But you need to actually get right to the limit, okay, or get right to the edge of where this graph starts. So notice we're plugging it into the parabola equation, so 0 squared is just 0. Okay, be careful, make sure you do squared first, right? If you square 1, you get 1, and then you tack on the negative sign. So it's actually -1. Same thing with 2, you square 2 first, which is 4, and then you tack on the negative, so it's -4. So here is what the parabola portion looks like. There's an open circle at 0, 0, being kind of big and obnoxious with that. There's a point at 1, -1. There's a point at 2, -4, so I need to go down maybe one more. Okay, and then I know that this shape is going to be a parabola curve. So notice anywhere where you make the change from one pattern to the next, that point is actually going to show up on both graphs. So it shows up here and here, but one of them will be open and one of them will not be open. Okay, well, generally. Actually, they both could be open, but they can't both be closed or the graph will fail the vertical line test. So keep that in mind. Okay, so let's practice one more of those. And again, it's helpful if you kind of already know what the graph shape you're expecting is, or shapes. So let's say that my two patterns are absolute value of x and -x plus 4. So we use the first pattern when x is less than 2, and we use the second pattern when x is greater than or equal to 2. Okay, so notice we should know what shape this graph will be, right? Absolute value graphs are V-shape. And then plain old x to the first power graphs are lines. Okay, so we're going to have a V shape followed by a line. Okay, we know that our piecewise function is going to look like that. So again, we set up two XY charts because we have two different shapes to our graphs. Okay, this one's going to be for x is less than 2, and this is going to be for x is greater than or equal to 2. Okay, so this one's going to be a V shape, and this one's going to be a line. Okay, so that we already kind of know what to expect. So we want to pick some things that are less than 2, okay, and you want to pick at least maybe one negative number. So I'm going to pick -1, 0, 1, and 2. Remember, we always butt up to this changing value here, but this time this one's going to be open, right, because it's only less than 2. It's not less than or equal to 2. Okay, so don't overthink these. The function is just absolute value of x. In other words, find the absolute value of all these numbers. So the absolute value of -1 is 1. Absolute value of 0 is 0. The absolute value of 1 is 1 again. And then the absolute value of 2 is 2. So we're going to graph this a piece at a time, and remember what we're expecting. We're expecting a V shape, although it's going to be a partial V shape because it's a piecewise function. So here are my points: -1, 1, 0, 0, 1, 1, and then 2, 2 is open. It's open because, again, this is plain old less than 2. So my V is going to track back this way, but this way it's going to go up forever. So we stop here, but we continue the other direction forever. So notice this is my V shape. Okay, so I'm expecting the next piece to look like a line, right? So make that look like a V instead of, I think my V kind of looked like a U there. All right, so now let's pick some things that are bigger than 2, so maybe 2, 3, and 4. Okay, notice here it's going to be solid, right? But I repeat this 2 value in both charts. Okay, but it's okay because one of the values is open and one of them is closed. So this time I use the second equation, so -2 plus 4 is 2, -3 plus 4 is 1, -4 plus 4 is 0. So notice in this graph, something kind of weird happens. I actually have to go back over my open circle, and that's all right, as long as I continue to have a function. And so it looks like I just have a line going this way then. So I have my V shape followed by my line. Okay, so notice the difference in this piecewise function is actually that I didn't end up with a gap like I did here because the pieces overlapped. Okay, so piecewise functions can look like either one of these types. They can look like kind of disjointed pieces where you have some gaps in the graph, or sometimes, very rarely, occasionally, they'll lie on top of each other and it won't end up with a gap at all. Notice both of these graphs still pass vertical line tests though. Okay, you could not draw a vertical line in either case that would hit the graph more than once, so we're still good to go as far as that goes. Okay, so what if you're given a graph and I ask you to write the pattern? So generally when you see these type questions, you probably will notice that they're not going to be super complicated functions. Okay, but what if I give you a graph that looks like this? So let's make an open circle at 1, -2, and kind of take the graph back this way. And then let's make a closed circle at 1, 3, and then go this way. Okay, so notice I have 2 horizontal lines. Okay. So it's helpful if you think of them as separate functions, because they really are. They're separate pieces / functions. So we're going to have a stack of 2, right? We just need to decide when it is that we make the change. Okay, so if we go from left to right, notice that the first function is just sticking around at -2, right? So it's actually y equals -2, okay? But it stays like that for all the x's that are what? So now you need to pay attention to, like, when does it stop being equal to -2? It stops at 1. So for x is less than 1, okay? Notice not less than or equal to because it's open. I'm going to stay at -2. Okay, but then the pattern switches to what y value? It switches to 3, and this would be for anything that is greater than or equal to 1 for x. Okay, because notice this is open, so we use an open circle. This is closed, so I use a closed circle. Okay, so notice like number 8 is the backwards version of 6 and 7. 6 and 7, I give you an equation and I say, hey, graph this. In number 8, I'm going to give you a graph and I'm going to say, give me the equation for it. Okay. All right, so one more piecewise function and then we're going to look at something else. So this is going to be kind of a dated problem because cell phone plans generally don't work like this anymore. But this is definitely how they used to work. Okay, so let's say that an old school plan, maybe that your grandparents still have or something, offers up to 500 minutes for $30 per month. And then after that, charges a fee per minute. They used to charge texts like this too. Like you got a certain number of texts per month, and then anything over that, you had to pay a fee per text, which really sucked if you sent too many. All right, so we're going to let C of x represent cost. Notice that's function notation, and we use C because we're speaking about cost. So C of x is going to be the cost of the bill, and we're going to use x to represent the number of minutes used. And I want you to write a piecewise function. So again, I'm asking you to take some information and write your own piecewise function, which is usually a little tougher than taking a piecewise function that's already in existence and doing something with it. So the first thing is they told us what to call things, so we're going to call our function C of x. Okay, and then we're going to have a curly brace indicating that, hey, we're going to have more than one pattern. So let's think about this. There are two different kind of versions of your cell phone bill. The first one is very simple. If you talk 500 minutes or less, your charges is plain old $30. Okay, so your cost is going to be $30 as long as the minutes you talk stay between 0 and 500. Notice it's kind of implied, right? But we can't talk a negative number of minutes. So the least amount of minutes you could talk is 0. The most amount of minutes without an extra charge that you can talk is 500. Okay? So as long as you follow the rules, right, you only have a $30 bill, you're good to go. But what if you go over? Okay, so let's talk about that. If you go over, you have $30 per month, but then you also pay an extra 5 cents per minute over 500. Okay, so we need to be, first of all, we have to start out off with 30 plus something. Okay, because the $30 charge is there no matter what. Okay, it's fixed. But then we want to charge 5 cents, but we don't want to charge 5 cents for every minute, right? X represents the total number of minutes that you use. You only want to charge 5 cents for any minute that's over 500. Okay, so how we could write that is we can say 0.05 for 5 cents, and then rather than saying times X, we're going to say times parentheses X minus 500. Okay, so let's think about why that will work. If you talked for, say, 550 minutes, okay, then you went 50 minutes over, and so you would do 550 minus 500, and that would be 50, and you'd be being charged for those 50 extra minutes. Okay, and so notice that will work. And this is going to be for anything over 500. Okay, so even if you were 1 minute over, right, that would make X 501, and then you do 501 minus 500, which is 1 extra minute, and it's the 1 extra minute that would get that 5 cent charge. Okay, so anytime there's a pattern change, we show it like this. We show it like a piecewise function. Okay, so some more on the graphs of functions. Functions can be increasing, decreasing, constant, or likely it will be a combination of these. In other words, a graph usually doesn't, steadily go up or steadily go down. Okay, usually it's a combination of sometimes it's going up and sometimes it's going down. Okay, so here are some guides for how we're going to write increasing and decreasing. First of all, we're going to use interval notation. We are not going to write from point, whatever to point whatever, then it's increasing and decreasing. We're going to use interval notation instead. Okay, so one kind of thing with increasing, decreasing, and constant, we only use parentheses. We never use brackets. Okay, I'm going to tell you why here in a minute, but for now, let's just write that down. And you only look at the x values. In other words, we only care about how the x-axis is split up when we're looking at increasing or decreasing from left to right. Okay, so let's do one example. You're going to need to graph this with me, but I want you to give the intervals where this graph is increasing, where it's decreasing, and where it's constant. So let's sketch a graph. Let's go out 5 in every direction. Okay, and I'm going to do what I normally do. I'm going to write what points I want you to have. So I want you to graph the following points, and then we'll connect the dots. -4, 4. -1, -2. 2, -2. And 3, 0. Okay, so if we'll graph these points, so -4, 4 is up here. Again, you can always pause the video. -1, -2 is down here. 2 -2's here. And 3 zeros here. So I want there to be a flat piece here. Do that right there. And then hit this point and then go back down. Okay, so pause it, and again, just make sure that your graph matches up with mine by graphing the points first and then connecting them. And so we're going to determine where is this thing increasing, where is it decreasing, and then where is it constant. On connect, it may not be all of these things. Okay, so if you find you have a graph that is not decreasing or it's not constant anywhere, then you would just choose none for that one. Okay, so you should have drawn the graph by now. If not, pause the video and get there. But you look at a graph from left to right like you read a sentence. Okay, so remember, we only care about the x values, right? So the first piece is decreasing. So we can kind of write this if we want. This piece is decreasing. This piece is constant. This piece is increasing, and then this piece is decreasing. Okay, so now we just need to figure out how we're going to write that, right? So remember, we only care about x values. So we start decreasing at x equals -4, okay, and we stop decreasing at x equals -1. Okay, we only list x values. We don't care about y values in this particular type of interval notation. Okay, and then notice we are constant from x equals -1 until we hit x equals 2. Oops, I put that in the wrong spot. So that should go in the constant spot. And actually, I put that in the wrong spot too, didn't I? All right. Normally, I would write them in a different order. That's why I weirded out with that. So we are decreasing from -4 to -1. I just wrote that in the wrong spot. And then we are constant from -1 to 2. Okay. And then we are increasing from, it looks like, 2 to 3. Which, technically speaking, I think I wrote my point at 4. So, eek. Let me fix my graph here. So I was only supposed to go to 4 here. I just goofed up on that and then do that. This is still increasing and this is still decreasing. I just put my points at the wrong spot. But from 2 to 3, it's increasing from x equals 2 to x equals 3. And then notice it starts decreasing again. Okay, so we use the union symbol and it decreases from x equals 3 to x equals infinity. Okay, we don't use negative infinity because we don't care that it's going down. We care that it's going to the right forever. Okay, remember, we only care about x values here. The y value is certainly going to negative infinity, but that's not what you're being asked to show with increasing, decreasing, and constant. Okay. So by the way, if you wonder why don't we use a bracket, so let's take a look at this point right here, kind of as you're finishing up. Notice if I look at this point, I could argue that it's the end of the decreasing segment or that it's the beginning of the constant segment. So the turning points we just don't include in either spot. So notice we didn't include it here and we don't include it here either because it actually could be a part of either one. All right, so the last topic for the lesson today is we're going to look at a type of max and min called the relative max and the relative min. I feel like we already know what max and min are, right? The min is a low point, the max is a high point, but adding the term relative in there just means that a relative minimum is the minimum on a certain interval. And the relative max is the maximum on a certain interval. I just cannot write today. Okay. So sometimes a graph doesn't have an overall max or min, but it might have a min if you looked on a certain interval. For instance, this graph. Okay, if you look back up here, and we're going to do another example in a minute. If I asked you to find the min, you'd have to say there's no min, right? Because this graph goes down forever. But if I asked you to look in the middle and tell me where the relative min is, this flat line here would be the relative min, right? Because it's the low point for the middle of the graph. Okay, so it's not the overall min, but it is the relative min. Okay, so for the last example, I want you to find the relative min and max. When it is plural, we use minima and maxima. So we don't say maximums, we say maxima. So here are the graphs that I want you to sketch. You don't need a lot of detail. So let's say you had a V graph shifted up 1 for the first graph. And then for the second graph, I want it to look kind of like a W shape. So let's go down to here also. So this is going to be kind of our base of our W, and so is this. And so the W shape is going to do something kind of like this. Okay, so let's first look at this V graph. Okay, notice that there is no relative max. Okay, there's not even a max if we only pay attention to a certain interval. There's just no max at all. It goes up both directions. There's no high point either way. Okay, but we would say that there's a relative min. So here's how we're going to say it kind of in two different ways. Okay, there's a relative min at 1, okay, or sorry, the relative min is 1 at x equals 0. In other words, we not only say how low it goes, but we say where it goes that low at, okay? Or if you want to, you can just enter it as the relative min is the point 0, 1. But Connect is going to want you to enter it this way, just so you know. Okay, but on a test or something, I'm okay if you just want to list it as a point. Okay, so that's version A. Let's look at graph B. Okay, so notice we don't have an overall max, right? The graph goes up in both directions. But what if we just looked at the center of the graph? I think we have a relative max. So we would say the relative max is 0 at x equals 0. In other words, the height is 0, but it's also at x equals 0. Or if you wanted to list it as a point, you could say 0, 0. But when we get to the min, notice that there are two values that kind of tie for the min. Okay, so notice these two values are both the low point, right? So we would say the relative min is located at a height of -2, okay? But we could say that's either at x equals -2 or x equals 2. Okay, so if you wanted to list those as points, there would be two of them, right? It would be -2, -2, or 2, -2. Okay, notice x value goes first, followed by y value. Okay, so this is going to be the way that Connect wants to see it, just so you know. But if you like the point version, I'm okay if you do that on a test.